Hello, in this video I will show you how to find the following limit. The method I will show today is based on a very simple trick. The very simple trick which is based on actually difference of squares identity. That's the identity like this. This is not the only way to solve this question. This is not the only way to find this limit. In my other video, you can find the link to that video in the description to this video. You can find more advanced, by far more advanced method, which is based on Taylor series and Taylor expansions, which is also applicable for this particular limit. But in this video, I will do very simple, very elementary approach based on this identity alone. Okay, so I will start by taking the function of which we need to find a limit, and I will transform this function a little bit into an expression which is more suitable for finding the limit, and I do so with the help of the difference of squares identity. My first step will be taking this expression and what I will do, I will treat this expression as if it's A take B. This is A and this is B. And I will introduce the second factor, which is A plus B. Here it is. And of course I will cancel that factor to ensure that we have identity in my relation. On my next step, I will take the enumerator and I will use the difference of squares. So I will condense this expression into the A squared take B squared. That's what we end up with if we do so. This is the A square. The square cancels the square root and x square is in here. You can cancel x square and x square in the enumerator and your expression becomes as simple as this. Once again, I'm doing some prep work before I can see what the limit is, and my prep work is based on the difference of squares identity. I will need to do one extra step to complete my prep work, and then we can actually see what the limit is. My step will be factoring. What I will factor x from the enumerator and I will factor x from the denominator. The result of this factoring is the expression like this. You see, my x as a factor was taken out from the denominator. What we're left with in the denominator is 1 because x is gone, 1 because x is gone, and 1 on x because x is gone. So this is my final stage of my prep work. So if I aim to find the limit of this function, I equivalently can attempt to find the limit of this function because these two are identical. That's what I'm saying here. Rather than taking the limit of this, I will take the limit of this. And because of the continuity, I can actually bring this limit inside and put it next to the only appearance of x in my expression. Now I will need to make a reference. This is often happens in limits. You need to reference some knowledge from your prior studies, and the reference I need to make is that the limit of 1 on x when x goes to the infinity is 0. This is a fact we use from our prior knowledge. That's what I reflect on in this sentence. We use this fact, and once we use this fact, the expression becomes 1 on square root 1 plus 0 plus 1, which evaluates nicely to a half. And this is the value for the limit of this function, 1 on 2. This is a beautiful solution. It's an elementary solution. It relies on two things actually. It relies on this elementary trick based on difference of squares, and it relies on this other fact which we established elsewhere prior to attempting this question, and it delivers this beautiful result of a half. If you would like to see an alternative way to solve this question with a more advanced technique based on Taylor series. Have a look at the video, the link on which is in the description to this video. If you have any questions in relation to this solution, please leave a comment to this video. And if you would like to see more of this type of arguments, subscribe to my channel. Thank you and bye-bye.